channel. My name is Godwin. Yeah, in our last class we spoke about partial differentiation of multivariable functions, and I told you that in the class after that we shall be talking about optimization of multivariable functions. So that's what we are doing today. Now, optimization generally is all about efficiency. Okay, it's all about efficiency in the use of resources. That's what optimization is all about. Now, it might be you minimizing something, it might be you maximizing something. Now, in the aspect of cost of production, for example, optimization would mean that you minimize your cost in a way that you are, how do I put it now? You are producing at the least cost possible. Alright? Then optimization would mean in the aspect of revenue or profit that you should maximize your profit in a way that is the highest possible. Okay, so that's what optimization is all about. So you minimizing something that you don't, something undesirable or something that needs to be minimized to its barest minimum, right? And then you achieving or maximizing something positive or something great or whatever, like profit or revenue or sales, okay, whatever it is, to your maximum, or even production. Okay, you might want to maximize your production to its highest. So that's why optimization is divided into minimization and maximization. Okay, so if you ask to find the minimum values of the function, you ask to find the maximum, you could maximum values of the function, not minimum values rather. You could be asked to minimize a function, you could be asked to maximize a function. Alright, so that's what optimization is about. So it's all about efficiency. If you're using your stuff to be putting your stuff to the best use possible. Okay. Alright. So there are three conditions for optimizing multivariable functions. Now the first is giving z equals giving z as a function of x and y. So which is what's out there. Okay. So where x and y are the independent variables. Now what are the conditions? A. The first order partial derivatives must be equal to 0 at the same time to get the critical point. Okay, so we talked about the first order partial derivatives in the first video. So what this is essentially saying that for at the critical point, your zx, since we are using z as a function of x and y, must be equal to 0, and then your zy must be equal to 0. I spoke about this in one of our videos where we were talking about the usage of derivative or something like that. So the essence of doing that is to make sure that you have a stationary point. So your curve is either around this point. So when you draw a tangent here, the slope here is 0. Okay? Or your curve is maybe around here. Alright, so the slope here is also 0. So that's what you're essentially doing here. It means that the z, the x, right? Okay? So when you are differentiating ordinary, basically when you are differentiating, what you are finding is the slope. Okay, so here, to show that you have a minimum, maximum, whatever point, the point that you are on must be a stationary point. So when you differentiate again, okay, your second derivative will now tell you if it will give an idea if it's a maximum or a maximum, if it's a minimum or a maximum point. Minimum point in the sense that if you look at this is a minimum point, right? So after leaving this point, you start going up to show that this is really a minimum point. So when you differentiate the second time, your derivative should give you a positive number because this is not a positive slope. Alright, so that is why when you differentiate the second time, it must be plus, it must be greater than 0 to show that it's a minimum, to show that your function is minimum at that particular point. And look at this, okay, I've explained this multiple times. This point here is a stationary point as well, where the slope is 0. So when you differentiate the second time, when you find the second order derivative, you should have a negative value. That negative value is telling that you now have a negative slope. So if you are having a negative slope after a stationary point, definitely your curve is something like this. The point you are coming from is a maximum point. So that's just what all of this is all about. Okay, now number 2, the second order partial derivatives must both be negative for a relative maximum and positive for a relative minimum. So that's what I've just said there. For a relative maximum, when you differentiate the second time, it must be negative. So for you to establish that you have a minimum or a maximum, to have a minimum or a maximum point when you are dealing multivariable functions, the partial derivatives, the two partial derivatives, when you differentiate them the second time, you must have a value that is negative, that is lesser than 0 to establish a maximum point, and greater than 0, that is positive, to establish a minimum point. Now you have the third condition, which is the product of the second order partial derivatives must be greater than the square of the cross partials. So what it's telling is that your second order partial derivative with respect to x multiplied by second order partial derivative with respect to y, when you multiply it together, it must be greater than the square of the cross partials. Now some books will tell you it must be greater than the product of the cross partials. Now I have already mentioned it. I mentioned it in the last video where we saw it that zxy is the same thing as what zyx. So if you say this times this one, it's essentially saying just square. Alright, guys. So if you not see the video, you have to see it to understand this one. Alright, so that is the third condition. Now this third condition has babies. Okay, kind of. So it's saying that if zxx and zyy, if they are lesser than zxy squared, which is the point that we are talking about. Okay, it's not different. If these two are lesser than zxy squared, but each of them has the same sign. Each of them has the same sign. Okay, your function is going to be at an inflection point. Okay, it's going to be at an where it's just changing direction from, let's say, this way to this way. So you are going to be at an inflection point. All right. So when you are just changing your shape from one shape, you are moving this way, or just change this way. Alright, or you are probably moving this way and then you change, just kind of changing the direction, kind of. Okay, so you have if zxx is lesser than zxy squared, where zxx and zyy have the same signs, the function is at an inflection point. Now, if opposing signs, that is, if this way maybe plus and this way minus, so this is minus and this one is plus, then you'll be having a saddle point. Saddle, as if you are on a horse, as if you are on a horse, so saddle, S-A-D-D-L-E. Now, saddle points, I think for our students, I would also recommend a video from Khan Academy for you to understand what a saddle point is. So, whatever it is, saddle point is all about, you seeing the same point as a minimum or maximum, depending on how you are looking at it. So if you are looking at that point from this angle, it looks like a minimum point, or it is a minimum point. If you are looking at this from this other angle, it looks like a maximum point. So you are not really sure, is it a minimum or a maximum point? So that's what you call a saddle point. The point where, the function cannot be said to be at a minimum or at a maximum, because it depends on how you are looking at the graph. Okay, so that's just that. I don't think it's something that you really bother yourself with, at least in Economics 204. Or economics in 2011 or 2011. Alright. So what we are just saying, because what we need as economic students is how to apply these things in maximizing profit and minimizing losses, maximizing profit, maximizing revenue, minimizing costs. All of those things. Alright. So it's more or less we need the maximum and the minimum points more than this other one, but it's good to just know that they also exist. And if you are required to, deal with them, then no problem. So here we have optimized this function z as a function of xy, which is this. So you have to optimize it to tell us or to show whether it is you'll be having whether this function is going to be at a minimum, maximum, inflection point, or what have you. I have two examples here, but it depends on the time. Okay, so if I'm able to cover, if I have enough time, I can cover the two examples, and if I don't, I will just cover one. Okay. Alright, so which is just this. So what are we going to do? What do we need? We need zx to be 0, we need zy to be 0. So that means we need to get zx first. So zx, differentiate with respect to x, so then this is 60 minus 4y. So you have 60 minus 4y. Then where's x again? X is here, minus 12x. So that's zx. How about zy? Zy is going to be 34 minus 4x. 34 minus 4x. Okay, then you have y here. Okay, minus 6y. Okay, so the first order condition, FOC, says that zx, zy should be set to 0. Okay, so when you do that, this let me call this equation 1, equation 2. So equation 1, let me see if I'm not 60 minus 4 minus 12x, 34 minus 4x minus 6y. When you set this to 0, so you have it will become 12x plus 4y equals 60. That's equation 3. And when you set this one to 0, you'll be having 4x plus 6y equals 34. That's equation 4. Okay, now you can just pick any of them. You can just, which one did I pick here? So you can say because of consistency. Okay, so I said, when 0 is 0, we add these. When from equation 5, okay, well, yeah, equation 4, 4x equals 34 minus 4y. Okay, let me use this. So from equation 4, so you have 4x equals this. So 4x will be equal to 34 minus 6y. So when you divide through by 4, x will equal 34 divided by 4 is 8.5 from what I have here. So you have 8.5 minus 1.5y, which is equation 5. So what does have this is you got equation 5 from equation 4. Substitute equation 4 in equation 3. Okay, substitute equation 4 is equation 5 in equation 3. So when you substitute that, and substitute equation 5 in 3, so this here, so you're having 12x. 12 is the x now. Okay, 12 into brackets. 12 into brackets. What we have here, 8.5 minus 1.5y. And 1.5y, in that's all, has 12x, then plus 4y equals 60. So 12 multiplied by 8.5, okay, will give us 102. So you have 102, so it's not clear. 102 minus 12 times 1.5, is that around 9 or 8 or something? Okay, 18y. Okay, 18y plus 4y equals 60. Okay, so here you have minus 18y plus 4y minus 14y equals 60 minus 102. So you have minus 14y equals minus 42. So this cancels this, and y just divided by 14, and y equals 3. So if y is 3, you just substitute the value of y in equation 5. Y is 3, substitute the value of y in equation 5. So substitute the value of y, substitute y equals 3 in equation 5. Okay, so which is here. So x will then be equal to 8.5 minus 1.5 into bracket 3. 1.5 times 6 is 4.5, so 8.5 minus 4.5 is 4. So you have this point. I think I like writing this way just to summarize the answer. Xy is 4,3. Okay, so these are the numbers that you need after optimizing this particular function. So now with these numbers, how are we now going to show this with a minimum or a maximum point? So to show that, we'll be needing zxx, zyy. Okay, zxx, zyy. See if they are both greater than 0 or they are both lesser than 0. So what is zxx? So we are differentiating this guy with respect to x again. So zxx will then be equal to minus 12. Then zyy is going to be equal to this zy with respect to y minus 6. So you can see that here both zxx and zyy are lesser than 0. Okay, because they are both negative. So this is telling us that, and if they are both negative, what is that? You have a relative maximum. Okay, so the points, so at the point where x is 4 and y is 3, this particular function is at a relative maximum. So that's, we need to write that. Okay, I've just said we need to write that. So that's the way to summarize. At the point where x is 4 and y is 3, okay, this function is at a relative maximum. But now let us see if that is indeed the case. Okay, so that then we now need our third condition. Okay, we need to look at our third condition, which says that zxx and zyy, are they greater than this or they are lesser than it? Since what we are talking is that, so we need to what c. So we need to know I think we already have our zxx, right? We have our zxx, we have our zyy, so we just multiply that, and we need to know our zxy. So zxy is you differentiating zx with respect to y. Okay, when you do that, when you differentiate zx with respect to y, we'll be having minus 4. Okay, if you decide to differentiate z by respect to x, you have x here, it's still minus 4. Okay, that's what it's supposed to be. So zxy is minus 4. So definitely zxy squared is going to be equal to what? 16. Please don't write it like this. Don't write zxy squared like this. You are not, it's what you are saying here is not easy. Alright, this is how to write it. It's equal to 16. So now let us see. Zxx times zxy. Zxx times zxy. So zxx is minus 12, z by y is minus 6. Okay, so zxx times zyy is equal to minus 12 times minus 6, which is 72. So from here, 72 is of course greater than 16. 72 is greater than 16. So what condition does, what's that telling us? Okay, if 72 is greater than 16, then we've been able to establish that this is greater than this. If 72 is greater than 16, and we have initial result that was able to tell us that we are operating at a relative maximum. For us to have a relative maximum and still have this condition, okay, where 72 is greater than 16, where this is greater than this. So definitely the function is not only at a relative maximum, it is actually at a global maximum. Okay, so those three conditions, whatever this is happening to strengthen whatever result you have from your second order condition. Okay, so it's going to be establishing whether it is global or not. Alright. So here, where the function is at a global maximum, the function, what is it? Zxy that we have here, Zxy is at a global maximum, right? And the global maximum where xy equals 4, 3. Okay. So what do we mean when we say global maximum? You must have come across business cycles before. Okay, but like I said, this shouldn't be your first class in calculus. So if you are economic students, you've likely done 1 or 2 macroeconomics, and from them you've been able to come across a business cycle. Let's say you have something like this, like this, like this, like this. This is a relative maximum. This is a relative maximum. This is a relative maximum, but this is the highest. This is a global maximum. So that means that comes around this function where x and y are giving us, where you have this coordinates, the function is around something like this. I'm not saying this is how the curve is essentially. I'm just trying to explain the difference between the relative maximum and the relative and the global maximum. So the function is around something like this, so which means that here, if this were a profit function, for example, you can easily conclude from what you've done that the function, that the profit is maximized, that is, and the firm is obtaining the maximum profit possible, alright, that it can, given that function, alright. If you have a constraint, when I mean constraint optimization, so you say that if it's a profit function and then you have a constraint, okay, so the conclusion will be that the profit is maximized, okay, where the values of, it might be quantities then, okay, where the value of maybe Q1 and Q2 where, so let's say this is Q1 and Q2, and where the values of Q1 and Q2 are 4 and 3, okay, respectively, alright, given the profit function as well as the constraints. Okay, so that's how to conclude. That conclusion is very important. I'm serious. Okay, your lecturer, your teacher will be looking for that conclusion, so you need to know how to conclude. Okay, so that's about that. So the next thing that we're going to do now is to give an assignment. Like I said, I'm already out of time, so it's to give an assignment. Okay, I'm going to write on the board in a bit. Here is the assignment. So given TR as a total revenue function, being a function of Q1 and Q2, two products, obviously, equaling 72 Q2 minus 2 Q1 squared minus 3 Q2 squared plus 48 Q1 minus 6 Q1 Q2. A, optimize the total revenue function. B, is total revenue maximized? Okay, show your proof. If it is maximized, you show your proof. If it is not maximized, you show your proof. Alright, so that's about that. And I forgot to mention something here. I already mentioned global maximum. Here is a minimum. Here is a minimum. Here is another maximum. But this is a global minimum. Okay, so for you to establish a global minimum from your second order condition, okay, your if it were like the function we had now, if it were going to be a global minimum, your zxx and your zyy would have both been greater than 0. Alright. And the third point, which is this, if this happens to be like this, then it's just going to, if this if zxx and zyy happen to be greater than the zxy squared, so that is going to be an establishing fact that the functional point is a global minimum. Okay, so if you have any question, the comment section is there for you to ask your questions. You can reach out to us on WhatsApp. Obviously, you can always reach out to us on WhatsApp as one of our students. Then this assignment you need to submit it as well as one of our students. So that's that about that. See you in the next video. Thank you for watching.